Okay. So I just clicked that live button. That's always interesting, of course. Just looking at the actual live stream on YouTube to make sure that everything's running smoothly, but I think we're kind of all right. Kind of all right. Yep. Okay. One final check if, yeah, I can see my mouse cursor now move on the screen. So that's all looking good. One final check if that's also happening on the YouTube side of things, but if that's the case, then we can go ahead and get started. Kind of all right. Good. Okay, so I think that definitely works out nicely. So that means that we can go ahead and talk about something rather cool. So a few weeks ago, I saw a message from the maintainer of sentence transformers that we now have a new version of sentence transformers. And it's a package that I've definitely used a whole lot. It's something that I have inside of a tool called embetter. That is a tool that I made for scikit-learn. It basically allows you to just have a whole bunch of embeddings be available in a scikit-learn pipeline. Yeah, there's just a bunch of new features in this library. So what I figured I might do is talk a little bit about what I think makes sentence transformers interesting, kind of from like an embedding perspective. Just the way that those models are trained is, yeah, they introduced a new way of training things, which I thought was good. But also recently, there's been a bit of a focus on getting embeddings that are lightweight to store on disk or to store in a database, so to say. And there's just a couple of techniques that are being used there that are just very interesting and nice. So I will zoom in on that. But first, I want to talk about this one thing that sentence transformers does that also causes these embeddings to be pretty good. So back in the yay old days, what you might have is, let's say, some sort of a use case where, let's say, there's an image. So you've got some sort of image that goes through a neural network, and then at some point you're going to make some sort of a prediction. So is it a cat? Yes, no. That could be some sort of a prediction that you could make. And then this neural network, of course, would have like lots of inputs on one end, and then it would have less inputs and less inputs. But at some point, you would have this layer, sort of feed forward style, right? But at some point, you would have some sort of intermediate representation here, and you could say, well, that's the embedding. In the case that you're training a system with just one label, so to say, that's not going to be terribly interesting. But you can imagine if you've got, let's say, many labels of many different classes that you might be interested in, then you might be able to get an embedding that's somewhat general. But it's still very much derived from a very classical classification task. So we have this label. Is it a thing? Yes, no. And that's the way you train these things. Now, one of the things that sentence transformers introduced was just kind of a redefinition of the way you go about embeddings, because originally the embeddings were kind of a side effect of a classification task, and people were kind of wondering, well, what if the task itself is to get a useful embedding? Maybe we can come up with a slightly different architecture that allows for that. So one approach that you could take instead is that you have some sort of sentence, and you're going to just pass that through some feed forward layers, let's say, or maybe a transformer, but you're going to apply some neural network stuff that goes feed forward. And also, by the way, this sentence is going through like bag of words, and we're going to get a numerical representation out. But the main point is we still have a neural network for that one sentence. Then we do the same thing for that other sentence that is also going through layers of sorts, right? And then at the end over here, we're going to ask the question, are these two similar? Yes, no. Yes, and no. So you would still get kind of like a binary classification going out over here. But one thing that's kind of interesting is you can definitely still get a gradient update, right? So we can definitely, by using this similarity measure, we can say yes or no, and we can push the weights to go into a certain direction. What we can also do is we can choose to maybe have the way that we embed over here be the same as the way that we embed over here. So these are kind of like the same architecture, they're just repeated. So that is also something we could choose to do if we wanted to. But the main flexibility, and I would argue also the main freedom that this gives you, is that you're very flexible in terms of what does similarity mean here. So just to give an example, one thing you could theoretically do is you could take your classification problem and you could say, well, if two sentences are part of the same class, then they are similar. And if they are not part of the same class, they are dissimilar. And what you could do is you could just take a whole bunch of random classification data sets, turn them into similarity tasks, and before you know it, you've got a big data set that you can train embeddings on. Another thing you could do is you could do something with distances in text. So if you've got two sentences that are, let's say, in the same paragraph, then that does say something about their similarity because they're close to each other. So you could take a sentence and another sentence, and if they are in the same paragraph, then yeah, they're similar. But if they're not, let's say, then you can say they're dissimilar. And this is kind of like an unsupervised way of just taking all of Wikipedia and sort of going with it. Another thing you could also do is you could also maybe think of search a little bit more. So maybe one sentence is more like a query, and the other sentence is more like a document. And you can say, well, that query and that document, they are similar. I have recently read a paper that also did something cool where you've got, let's say, I think they were using abstracts, but they were using academic articles. And you know how one article can have like a citation from one article to the next one. So if one article cites another article, you could also argue that maybe that has to do with similarity. And you kind of have a graph of this citation structure. So you could take the abstract of one paper and the abstract of another paper. Do they have a citation? Yes, no. That could be maybe the way you go about similarity. There's lots and lots of ways to really go about it, but from my perspective, like the main thing that the sentence transformer library brought to the table was to say, well, this is maybe better if you want to do embeddings than to sort of do a classification task and then use some sort of side effect of that as an embedding instead. Because if you construct your neural networks in a clever way, you can also come up with some numerical details that kind of matter. So I'm going to redraw this a little bit. So let's say we've got sentence 1 again and sentence 2 again. And again, I'm going to be a bit vague on the architecture here, but some amount of layers, some amount of transformers, some amount of feed-forward stuff, right? Like one thing that is also kind of cool that you could do with this architecture is you could say, well, I've got some embedding over here and I've got some embedding over here. Then I'm going to calculate the cosine similarity between them. And that's going to give me some sort of number, right? So 0.789, some sort of number. And then I've got my actual label. So that is going to be either, let's say, 1 or 0, or you have some sort of label, actually. And one thing that you could then do if you want to get your gradient update is you could basically just say, well, what's the mean squared error from like that cosine distance with the label that I've got over here? And like another kind of cool thing about doing it this way is that then if later on you're interested in using these embeddings in kind of a neural search kind of a thing, then you would really like the cosine distance to be the bit that is trained for, right? But by choosing your cost metric, sort of by choosing your loss function maybe this way, that you take the mean squared error over the cosine distance of these two sentences that are going in, you might also be able to get an embedding that will later behave more like you want it to as well. And if you're using the default trainers inside of sentence transformers, this is the stuff that's actually happening under the hood. So that's like an introduction. Like if you want to train your own thing, you can totally go nuts. The documentation's got you covered. But the real reason why sentence transformers these days is just so interesting is also because the training is pretty easy. So people just went nuts and trained all sorts of embeddings for you, so you don't have to do that yourself. So there's actually like a pretty, I would argue, substantial community of people really doing cool stuff with these embeddings, training them, sharing them, all good stuff. But that then brings us to maybe the next problem, which is how do you store them? So I have some sort of text in general that's going to go through a sentence transformer, so to say, and that has to go into some sort of a data store at some point. And then I'm going to assume that we're going to be doing some sort of a approximate nearest neighbor thing here, maybe later as well. But even if you're not doing that, storing it in a database makes a lot of sense because taking your text and encoding it is computationally pretty expensive. Like if you've got a million sentences, this actually does take a small while, especially if you've not got a GPU. But if you've got multiple millions of texts and sentences and whatnot, then you do want to store this on disk. And then it also becomes kind of beneficial if you can come up with techniques where it doesn't take up as much disk space, but can still perform the approximate nearest neighbor thing. So there are some relatively recent techniques inside of sentence transformers on this domain, and that's the thing I really wanted to dive into in this live stream. So I prepared a little bit of code, but I do hope that this, as an introduction, covers a lot of ground and that people sort of understand that there's stuff to really like about sentence transformers. I may dive into the training bit in a separate live stream as well, but I think doing techniques for properly storing these things is also pretty interesting too. So, as a motivating example, what I've done is I've downloaded a data set up front, and this is a data set that contains many recipe names. So let's just have a quick look at that. So a long, this is really a long list of names. But these are barely sentences, right? But you do have stuff like pork chop noodle soup, and there's pork in there, so it's a meat dish. So you can assume that maybe dishes that are also meat dishes are similar to this dish. And this is where the neural sort of approximate nearest neighbor thing might actually be super kind of useful. So I have a whole lot of these recipe names. That's all well and good. And what I can then go ahead and do is I can take those recipe names and I can pass them through a sentence transformer. Now, I'm going to take a very specific sentence transformer in this case, and it becomes clear later on why. But there's Tom, he has this one sentence transformer over here that's trained on a specific data set. From sentence transformers, you can load the sentence transformer object, you can pass a string, which is kind of like the name. I believe this is his Hugging Face name, and then this is sort of a repo name on his Hugging Face account. But either way, the recipe names go in here. I then get this a big array out. So I have about 6,000 sentences that went in. Every time I do an embedding, I have about 760 dimensions that go out for every single sentence. So, I get a pretty big sentence array out. And it takes about 30 seconds for me to sort of parse through this. So again, you could speed this up with a GPU, but I do hope to point out this is compute intensive. What we probably want to do now is store this on disk so we don't recompute this again. And it will be nice if we can store this on disk in a way that's computationally not super duper expensive. So, okay, what can we do to maybe help with that? Like, what can we do that such that we can maybe not store as much information? Like, one thing you could do is you could maybe do something with principal component analysis. You could say, well, these are embeddings. These are very, very wide, and maybe we can do something with principal component analysis, such that we just don't store every single item. We just store a subset. And that's fair. That's something you could do. But maybe we can also do something clever during training. And that's what these Matryoshka embeddings do. And I would like to explain that before showing you the results. But there's something we can do during the training of a sentence transformer such that it's easier to throw away data later. But I got to draw that a little bit. So, okay. Let's say that, again, we have some sort of sentence that goes in, right? So S1, some sort of sentence. And I have, again, some I'll be vague, neural network structure. And out of this comes some sort of a embedding, let's say. And let's draw that a bit bigger. So let's say this is an embedding of size, what did we have? 768. So this is a very, very, very big embedding. Well, then what you might be able to get is, as a next step, as I showed you earlier in the training diagram, is that this is going to be used to do something with cosine similarity. And that's going to cause the label, and that's going to cause the backprop, and that's going to do the gradient update. That's all going to come good out of this guy. But what if I actually split this up a bit? So I'm not going to take the entire array just yet. What I'm actually going to do instead is I'm going to say, well, technically I have this big array that comes out, but I could take the first 64 items, right? And what I could also do is maybe take the first 128 items. And, maybe not all of them quite yet, but let's say that I've got the next 256. And then over here, I've still got my, my big one over here. But one thing I could also do now at this point, like if I just take the first little chunk and if I consider that I still have the one big array that I started with, but if I just have maybe 4 arrays now with little subsets, then what I could theoretically just do is I could say, well, let's calculate the cosine similarity here and pass that forward, and that gives me a loss. I could also do that for this guy over here. Again, I have a cosine similarity, and I'm going to calculate a loss. I'm going to do that for this guy as well. And technically, looking at this, you might say, well, okay, Vincent, this is going to result in 4 loss functions. And then just as a hack, let's just add them together. So we have these 4 cosine losses that we're just going to add together. And that's going to be the total loss that this system is going to optimize for. So again, that means that I get some sort of gradient update over here. I get some sort of gradient update over there, over here, and over here as well. Note that the gradient updates, because, some of the weights that I have over here are actually from this bit originally. So we are going to get gradient updates in some regions of that embedding over here that get, this part of the embedding is going to get more updates, let's say, than maybe this part of the embedding. But technically what kind of happens if you do that, you also kind of imply that the first couple of dimensions of the embedding are also just more important. Because just those dimensions on its own should also yield a pretty good cosine similarity. And then you might be able to get more information. So the next cosine similarity might be a better fit because there's more information known. But by training the system kind of in this way, you do get this interesting side effect that in layman's terms, the first few items that you train on, those can be seen as sort of the bit that gets the most updates and therefore the most important. Like more information is stored there per dimension than maybe over here. And this is something that people like to call a Matryoshka embedding. Those are those, I believe they're Russian dolls that you can open them up and there's like another little one in there and you can keep opening it up. And it's kind of something similar happening here in a way. Like this is the innermost model. We can add a little bit over that. We can add a little bit over that. We can kind of add a little bit over that. But this is sort of where the name Matryoshka kind of comes from. Or at least this is, as I understand it from reading the docs. So this I thought was like pretty interesting and curious. Let's go back. But I thought let's actually see if we can benchmark this using this this food data set. So again, what I've got here is some original model, and here I've got the Matryoshka trained variant model instead. And I see that is the screen updating? Yeah, it's updating. Good. So again, this is the original model. This is sort of the base model. The original model is called TFM base, and that produces this XTFM. So these are the embeddings from this base model. And I'm doing the same thing down below here, but for Matryoshka. So this is the Matryoshka transformer, and these are the Matryoshka embeddings that I get out. These Matryoshka embeddings have the exact same shape as the base embeddings. It's just that I should be able to cut information out from them and get something that still holds a lot of information without having to do PCA in hindsight. So again, same shape, we can see that. What we can also do, and I thought that was kind of cool, is I could just say, look, let's calculate all the cosine similarities between the matrices themselves, and we can see that there's lots of different values, and these two histograms kind of have the same shape, so it checks out. We get similar performance, not 100% the same, but fair enough. But then I start doing something that I think is pretty interesting, and it's also a little bit more complex. That's down below here. So remember, I have my original embeddings and I have my Matryoshka embeddings. And what I'm now saying is I'm going to loop over this integer I, and I'm saying, well, first I'm going to grab the first 32 embeddings from this big set that I had over here. So I'm not doing anything with the rows, but I am saying let's take the first 32 dimensions of this embedding over here. So this is much less wide than what I had before. And I'm calculating the cosine similarity using scikit-learn. And I'm taking all of the vectors that I have and I'm comparing them to all of these other vectors that I have. But I am definitely also losing information over here. Right? So you could argue over here that we have less dimensions to go on, so this cosine similarity that I get out on this reduced form could be seen as maybe less reliable. That's sort of a concern one might have. Now, what you can do, of course, is you could also then wonder, well, I have these cosine similarities, and I could, if I have this big number over here, then I just have the normal cosine similarities that I would have normally. But you could wonder, how does this... How do the cosines? I should rephrase. The main thing I'm going to answer now is I have all these cosine similarities. I know what they're like when I use all of my dimensions, and I can check how much of that information is intact if I only use 32 of them. That's what I'm going to sort of try to plot. And I'm going to compare the base situation with the situation with the Matryoshka embeddings. And the way that I'm going to calculate that is by just using correlation. So I'm just going to say, hey, if I have less dimensions, do my reduced dimension cosine similarities still correlate with the situation where I don't remove any dimensions whatsoever? Because if they correlate very nicely, then it would be cool to confirm if this Matryoshka situation, if the extra effort we took in training actually allow us to store less dimensions on disk. So so this ran up front, right? So we don't have to rerun that again. But here's the basic chart with the results of that exercise. So again, on the x-axis over here, you see the number of dimensions that I've picked. In a situation where I just take all of the dimensions that are available, it's like 760 something. Then, I have perfect correlation. But the more dimensions I start removing, you do see that, the less and less correlation that I get. And that's also something I would totally expect. If I throw away, let's say, almost half of my dimensions, then there's still a lot of correlation, but you can just see that it plummets to zero pretty quickly once we get closer and closer to zero. But the main difference here is that if I were to repeat this exercise with the Matryoshka embeddings compared to the base embeddings, then it does certainly seem that the Matryoshka embeddings are able to hold on to information for much longer compared to this just base model that didn't get that Matryoshka treatment. Now, why is that so interesting? Well, it basically means that if you have a model that's been trained with Matryoshka embeddings, then the training procedure might still be expensive. But once you've trained the thing, you can actually do this little empirical research a little bit better, where, okay, maybe I can make do with a little bit less accuracy. Maybe I care about having more of a compressed state a bit more. And you do get just a little bit of extra wiggle room if you use these Matryoshka embeddings. That's kind of the lesson out of all of this. And I thought it was kind of an interesting way of going about it. Now, I probably do want to suggest that if you're going to go down this direction, do check out what PCA might offer you as well. Because I do wonder if you do principal component analysis with this, if maybe that could yield pretty good results as well. I would imagine it does, but the downside of doing the PCA thing is that it doesn't really know what is similar or not similar in your data set, and that is information you can pass in during the training loop with these Matryoshka embeddings. So the main thing that my bad. So the main thing I've done so far is I have basically been able to reproduce something that is on the documentation page. So it might be good to show that actually. So toggle full screen. Sentence transformers Matryoshka. This is probably misspelled. There you go. Matryoshka embeddings. Like I'm using the same models as what they do here. I just have a slightly different data set. But you see like a very similar chart. Yeah, so they're truncating with it. But here you can also kind of see that. I guess the chart that I've got is definitely like more drastic than what you see over here. But you can confirm again that if you are using the Matryoshka embeddings, you do get this uplift. Like you do see that there's a difference between what the base model would do and what the model would do in the Matryoshka situation. Documentation also gives like a fair amount more details, but like if you want to train it, by the way, like there's a good, like it's a very easy short snippet. It's pretty good. But I thought this is an interesting idea. Like this is something that might be able to help you just have slightly less concerns with these with this dimension, and you should be able to store your data a lot more cheaply on disk. If there's time at the end of this live stream, I want to compare this to PCA now. Actually, I forgot to do that. I should probably do that in a bit. Yeah, so like Luke has a very good point. Like I do want to compare this with PCA after. There is, however, before I get to that, I do just kind of want to show. Let's toggle full screen on this guy. So like this is one technique, right? And I think it's a pretty neat technique, and there's stuff to like about it. But you could also wonder, well, is this the best that we could do? Because this doesn't, like, the downside of this approach also involves, like, a pretty big training run. Like, you might have to retrain the way that you train your embeddings because you have to use this Matryoshka stuff. And, you know, I still think it's a neat idea, and it definitely tickles my mind. But if I really start thinking about, hey, if I really want to just cut with a big axe and really get sort of dimensionality down, there's a different trick that we can do instead. And that is something that I'm showing in the code below here. So, sentence transformers, and this is a relatively new feature, also allows you to apply some quantization. And what does that mean? So, what I could do is I could do something like NP, and I just put some sort of number in here. So let's just some sort of floating point number, right? Oh, I should do NP, my bad, dot array. So this is a floating point number, right? And you could wonder, well, if I'm storing embeddings, do I really need a lot of numbers after the dot? Really here? Like, what kind of precision do I need? Do I really need this amount of precision, or can I maybe make do with, let's say, a few less digits? And the way that you store digits in a computer isn't exactly like digits behind the dot or the comma. It's a little bit more about like bits, but you can at least imagine the argument that maybe we don't need to be a super duper precise all over the place. And one kind of extreme version of that is to say, well, you know what? I'm only going to allow ones and zeros. I'm just going to say every single dimension, turn that into something binary. And the way that you could do that is you could say, well, take every floating point number, and if it's positive, it's 1, and if it's negative, it's 0. But we're just totally going to make everything binary. Turns out if you do that, you can actually do a whole bunch of tricks, because you can do bin packing. And that's something that I did that was also kind of like a cool trick that I wasn't aware of before. But you can also do some bin packing if you want. This bit is copied from the docs, but that's not relevant. So let's look at the code and what I'm doing. So I'm loading up the base sentence transformer model, this all mini LM L6v2. I believe this is pretty much the most lightweight model that you've got in sentence transformers, and it's still pretty reasonable. It works pretty well, but I have my model, I have my documents. My model will then encode the documents, and I get these embeddings going out. That's super cool. And then what I can do is I can use this quantize embeddings function. And the embeddings that you had before, that's what's going to go in. But you're also able to set a precision over here. And I am saying in this case, like, turn it into a binary representation. I believe this stands for unsigned binary. You can check the docs, there's like details, but the main thing that's important is I get these binary embeddings going out. Except that when you inspect the embeddings themselves, they are not binary at all. Like if I scroll down here, you can see that these embeddings, they're just integers, really. They're not ones and zeros what I get out from NumPy over here. I get some stuff that really does appear to be uint 8. So this is an 8-bit integer. And I can also check the shape. I have 1,000 examples, but we have so these binary embeddings, they're integers and they have dimensionality of 48. So one thing I can confirm, if I just take the number of bytes that are on the original embeddings and I compare them to the number of bytes that I have in these binary embeddings, like you can totally confirm, like the amount of information that I'm storing in memory is way smaller than what I had before. Just to sort of calculate the number. Like we're at the 3%-ish size of this thing we had before. So that's really, really good. So we are definitely like in lightweight land here, right? So that's good. But then what is the story here that these are not integer, that these are integers instead of being like proper binary? Well, the story there is that if you think about an 8-bit number, like how many bits can you put into that thing? Well, 8. So you can also maybe think about a binary array of like ones and zeros. If you have 8 of them in sequence, that can actually be represented as an 8-bit integer. And NumPy doesn't allow you to go lower than 8 bits. So there's no 4-bit integers, there's no 2-bit integers or anything like that. So this is kind of like the smallest number size that you can store. So what is actually happening internally is kind of like a data structure trick. Like if we have 8 binary bits, we just store them into a 8-bit integer instead. And NumPy actually allows you to sort of explore that with this unpack bits function. Turns out that if you want to have binaries stored in a NumPy array, this has been a very classical way of doing that. So what I could also do is I could say I want to unpack something. So I take my binary embeddings, and for each one of those rows with integers, I'm going to call this NumPy unpack bits function. I'm going to do that for all of the candidates that I've got. And when I do that, I get an embedding out. Hang on. So if I just look at this unpacked thing, then I do get my nice little binary representation. But the thing to remember is what you get out of the sentence transformer model here, these binary embeddings. Yes, they are stored as integers, but that's just because there's a very convenient bin packing trick that we'd like to use. So that's actually what's happening here. Just as a brain fart, like one thing I do want to kind of now do is if I just look at the first 10 numbers here, and if I compare that to the, I believe I called it, didn't I call that embeddings? Yeah, I call that embeddings. Take the first item, also look at the first 10 candidates there. Yeah, so I believe the way that they're going about it is if the number is negative, we get a 0, and if it's positive, we get a 1. Here it's negative again, 0, 0. Yeah, so the quantization technique here is kind of with a brute force. It's really just, is it positive? 1, is it negative? 0. But you get the binary representation here. Like that's the thing we're doing. We're turning something that's not binary into binary. Binary is like way lighter. So this is still kind of interesting because, you lose a whole bunch of information for sure, but we could wonder, how much do we lose? Because especially if we're doing something with cosine similarity, right? Like the thing that's going to matter a lot is the angle between two vectors. So even though this is kind of like a blunt reduction, if at least empirically we can demonstrate that we're not losing too much information, oh boy, we really can save a lot of disk space by doing this. So I've done a similar exercise. What I did is I took the first embedding from I've taken the unpacked thing and I've taken the normal embedding one. And I'm taking the first embedding from my set and I'm comparing it to all the other embeddings that I've got. Again, I'm doing cosine similarity. And again, I have my similar cosine similarities, my original cosine similarities in the vector here. So this is a vector with lots of cosine similarity numbers. And I'm doing the same thing with the unpacked representation that I made over here. So in short, these are all cosine similarities between items that I have in my original set. And here I'm again calculating the same thing. It's just I'm calculating the same thing on the binary representation. And if I were to just plot that, like if I take the original similarities, cosine similarities with the binary ones, it's not perfect, but it does totally correlate. So on the y-axis over here, you've got the original cosine values. And on the y-axis over here, you've got the cosine values if I apply like the binary quantization. And yeah, I mean, it's definitely not necessarily perfect, but there is definitely a correlation line over here. So you lose some information, but it's also not necessarily all over the place. And there is a kind of a mapping that you could apply. Like sure, the number over here is 60, but there is a pretty easy mapping to go from the sort of cosine number space over here to the cosine number space over there, so to say. And also, if I think about how people will use this, usually the cosine similarity is more meant to sort stuff later. Like you want to find the most similar items. And then the number itself doesn't necessarily care too much, as long as the number can still be used for ordering in a consistent way. And yeah, like again, this is you go from 100% to 3%. This is a pretty big reduction on disk. This may actually be pretty legit, depending on the use case, right? Depends on the recall, the number of items you want to retrieve, etc. But I did not expect this linear relationship to show up. Like this is actually pretty darn good. Not perfect, but pretty darn good. A thing to keep in mind is if you really want to do stuff with this, not every backend actually supports these bin-packed representations. So like if you want to use a approximate nearest neighbor database, you do need to have like some sort of database that knows how to deal with these bin-packed integers in order to get like the benefit out. One thing I did go ahead and do just for good measure, I had Leland McInnes on the podcast a few days ago, and he has this tool called Pine and Descent, where you can sort of write your own number function, and that can be the distance metric that is used for the retrieval. And what I actually did is I wrote a very fast number implementation to calculate the similarity between two bin-packed items. The way I'm doing this is I'm just calculating the bin-packed overlap, like how often is there a 1 or a 0 in one guy, and there's also a 1 or a 0 in the other guy? Like, when are they equal? I'm using like what happens if you use something like this in a number form? Would that also be good? And notice, by the way, what I'm doing in this number formula over here is like I'm literally taking an integer value, expanding that to the power of 8, and then taking the mod, and that way I'm also able to sort of retrieve the original 0 or 1 integers out. This is kind of like the unpacking thing, but doing it manually. But yeah, if you do it this way, you kind of get pretty much the same shape, but the number that you've got on the right-hand side over here is just really different. But one thing I do know for sure is that Pine and Descent would support a cost function like this. So if you want to do retrieval stuff in memory Binance Descent supports this quantized stuff out of the box. I believe LanceDB doesn't. I don't know about VVA, but that's like a thing you would have to check. Like this quantization trick is pretty neat, but your mileage may vary depending on the backend that you're using to retrieve your embeddings, so to say. But this is also, you know, pretty cool. I would say like this is it's definitely cool to see the sentence transformer package. It's been somewhat unmaintained for a while, but definitely the last year or so, there have been a few features that went in that feel like they're just a little bit experimental, but at the same time, the ideas just seem pretty sensible, and it's been pretty easy for me to just reproduce on a random data set that there is merit to these features. So that's definitely super cool to see, especially because all of these embeddings are like nice and open source. You don't have to send your data to OpenAI or anything like that. So like, definitely stuff to like. So those are the main things I actually wanted to show, and I believe there's still some time left. Yeah, there's definitely some time. What I think I want to do as part of the rest of the live stream is just compare this maybe to PCA. And I do think like that would be like a nice little thing to conclude with. But this would also be like a great point in time to ask questions. And someone in the live stream is saying that Tom Aarse is doing a great job. I totally agree. And I've also reached out to him with questions on LinkedIn, and he's a great sport. He's definitely helped me on a couple of personal projects and experiments as well. So he's definitely doing good work. One fun fact, I forget the name. Tom Aarse has also, there's this one classifier that uses sentence transformers under the hood. I'll look it up later, but sentence transformers isn't the only project where Tom is active in. He does a bunch, a lot of stuff on the Hugging Face side of things, but he's definitely very active there. So just to check, any questions about any of this? Because if not, then I'm gonna see if I can expand this chart so we can compare the Matryoshka performance with the PCA performance. I think that's kind of a thing I would like to maybe do as well. SetFit. Thank you. Tom has also been maintaining SetFit. And I think that's also how he eventually got into sentence transformers. Like he'd been maintaining SetFit for a while. And then after a while, I think SetFit couldn't really get a next update because some changes had to be made to sentence transformers, and I think that's how the ball eventually got rolling. Could be mistaken. Ask Tom if you really want to know for sure, but I believe that's the story. Okay. So Luke is asking a question about UMAP, and I can answer that one right away. So because there's a little bit of a danger with what Luke is suggesting there. So, okay, so there's a couple of dimensionality reduction techniques out there. So you've got PCA and you've got UMAP, but they do work fundamentally differently. PCA in the end is a linear mapping, and UMAP is very much a non-linear mapping. And if I think about the loss function, like what's the thing that both of these two techniques optimize? PCA just wants to say, well, there's global variance, and I want to have fewer dimensions, but I want the global variance to still be explained as well as possible. So you should expect global structures to still be in place. Because that's what the model will be punished for if it doesn't do that right. UMAP, on the other end, is more interested in the local stuff that's happening. So things that are close together in like locally in a cluster will remain close together in a low dimensional representation. PCA, on the other hand, tends to favor the global structure more. So stuff that's far away in the global structure, oh, there's the camera. Stuff that's far away in the global structure, that's what's going to remain far away in PCA land. But in UMAP, if two things are, let's say, close together in global structure, but they're part of two different clusters, they could really go far away in the 2D representation. That's just something I've noticed empirically, but also if you reason about the algorithms, this is also something that makes a lot of sense. So I don't mind giving UMAP a spin here, actually, but I hope that this explanation also helps emphasize that the mileage can definitely vary. So I'm interested in doing PCA first. But yeah, so there's a bunch of questions of people of liking me to try out some stuff, but I think I will just do the UMAP thing first, and then we'll see from there, right? So okay. Let's run code from scikit-learn decomposition import PCA, right? And I think, and I could be mistaken. Actually, let's just do the. This could be a bit slow for higher dimensions, so I'm just gonna reduce it down to here because PCA can get slow. But what I could do something over here is like do something like PCA, and then number of. Oh, I should run the line above, otherwise I don't get the autocomplete. But I believe I have something of a number of components available to me. So I'm going to set that to that. Then I am going to fit to the original input. I think that sounds fair. And then I'm going to transform set original input. So this would be PCA reduced. This would be the reduced form. I think that's safe to say. PCA out, but these aren't the, yeah, so these aren't the cosine similarities just yet. So I need to say something like PCA reduced over here equals cosine similarity, and then PCA out, and I'm going to grab the first no, actually I think I can just do this. Because the output of the PCA algorithm is already the right shape. So I think I should be able to do this. The only thing I shouldn't forget to do is maybe add the PCA at the bottom over here. PCA out. Oh no, PCA reduced, right? And just for good measure, I'm going to print I now, because this might actually take a while, and I do like to see a sign of life as stuff is sort of happening there. Yeah, this can definitely be slightly slow. That's okay though, because I also need to add a line of code here because I want to see the PCA results. And we're also going to add a name over here for the PCA results. So this is pretty exciting. We're going to wait for like, this might take a small bit, but then we should get the chart. Yeah, so it's printing, it's now training. Almost there. All right, that feels good. Exciting, exciting, exciting. Setting an array element with a sequence. What is there something happening on that level? What went wrong here? PCA reduced, ravel. Oh, right. Yeah, so it's not just a reduced form. We need to have the correlation. That's the thing that in the end we are interested in. Okay, so okay, so then PCA correlation is, I think, pretty much the same as what we've got over here, but we're going to compare the base sims with the PCA reduced. Yes. Okay, this is a yeah. Okay, so I will explain why we needed this after I hit run. So these are the cosine similarities that go out. We want to calculate those. That's good. What went wrong now? Okay, so let's inspect this then. So that definitely looks like a normal array. So far, so good. Oh, wait. Yeah, okay, this part makes no sense. yeah, that's sort of the downside of copying and pasting code when you're trying to be quick. You might copy something you don't want. But again, like I have these are the cosine similarities, of course, but I'm not necessarily just interested in those similarities. I want to see how they correlate with the base similarities if I have all the dimensions around. So that's why I need to do this one extra step. That's also what I'm doing over here. However, these should now be the PCA correlations. They are now actually going in here. So that should theoretically mean that once that stuff is now done, final step, I should be able to run this. Actually, this is interesting. Let's see if we can go even lower. I'm going to do something ridiculous. I'm going to go to 8 and 16 now as well. So the reason that I'm doing this, I do think it's interesting that PCA does seem to capture something. But yeah, it's also losing something. So if the dimensionality is quite high, PCA is actually losing quite a bit of information. But part of me is wondering if we go for super low dimensions, if then the PCA is actually able to hang on to something. Like one thing that does make a little bit of sense to me is that if I were to, thinking about UMAP again, so if you want to calculate the cosine similarity, you really like, okay, it's hard to really guess what's happening. Like, my worry is that if you do something with UMAP, that UMAP is just going to cluster the data a little bit too much, and it might actually be beneficial, but you might also lose information there. So that's why I'm not so super sure what would happen here. Oh, this is interesting. Okay, cool. So if you, so if you're interested in doing the utmost ridiculous thing and really sort of doing reduction, like if you're really interested in throwing away 95% of all your dimensions, then PCA becomes a bit better. But you could maybe also argue that, you've got 8 dimensions here out of like almost 800. So this is like a 1% of the information that's still left. You could argue that you're maybe more interested in being around here. I think this is like the 64 mark. This is still 8 times as small, but this definitely feels more reliable than PCA. Although I do think it's interesting to see how PCA is really, really flat here. It could be that PCA is really just focusing on the global structure. Not super sure what's going on there. I would have expected it to be just a little bit more up, maybe, but could run it for longer to know for sure, but that would probably take too much training time. I will put this code up on GitHub. We have this YouTube appendix. I'll add the link in the show notes. I think doing PCA was pretty fun. We don't have the time, I think, to do UMAP because UMAP does take a bit longer to train, but this was still interesting to confirm. And it's also nice to be able to confirm that the Matryoshka embeddings actually also, at least on this data set, definitely outperform PCA. That's definitely also good to just see. Cool. If there's any like quick questions, now would be an excellent point in time, but I also think it's kind of fair to maybe call it quits. This has been a pretty good good live stream in terms of information shared, so I'm pretty content. Interesting chart. Yeah, interesting chart. Well, yeah, especially when you consider, so doing it in binary might still be better in terms of like disk space and stuff, but it's also kind of hard to compare this chart with the one I've got below. So that's all work we can do later. But yeah. Cool. Then if there are no further questions, thanks for joining on a Saturday. I will definitely try to be back on Fridays from now on. Just sometimes like I have a family, I have a wife, I have a kid, and sometimes life gets in the way. But I'm happy to see so many people still show up on a Saturday. This is super cool. Let me know if there's other stuff you would like me to check out for later weeks. I'm definitely open to suggestions. And yeah, hope you all have a good weekend. Thanks for listening. I've just also sent that in a chat. So I'm going to stop the broadcast as well.